Okay, so let's continue. Now, our observation was the following. Okay, so I will not prove this theorem because this semester we are running out of time, but you can find the proof in the book. And there are several proofs of this because if you start looking at this as a generalization of the mean value theorem, then you get this one. But there you can find the error term by doing some integration also. You differentiate, integrate, find the error term. There are other forms of the error term. Okay, let's stick with this one. And our main observation is if we can understand the nth derivative and bound it, then the function is analytic. So this immediately suggests that sine and cosine are analytic functions because their nth derivatives are bounded everywhere. Okay? So that will be a major gain, not on some interval. Okay? So your function may be such that its nth derivative is unbounded, but if you look at it at bounded intervals, it may be bounded. Then the function will be analytic there. Okay, so okay, so consider now sine x. Okay, the nth derivative is plus or minus sine x or plus or minus cosine x. Okay, so let us call this f of x so that I can refer to it. Hence, the absolute value of the nth derivative evaluated at any point is less than or equal to 1 for any x in R. Okay, so sine x is analytic everywhere. So this means if I write the Taylor series expansion now, the Taylor series expansion converges everywhere to sine x. Okay, so let's start writing the Taylor series expansion. So f of x, the zeroth derivative is sine x. Of course, we prefer to write these Taylor expansions around x equals 0 unless we have spatial need, because that gives the general picture with less notation. Okay, so I evaluate this at 0, I get 0. Okay, I take the first derivative, I get cosine x. I evaluate the first derivative at 0, I get 1. I get the second derivative minus sine x. Second derivative at 0 is 0. I take the third derivative, so this is minus cosine x. The value is minus 1. I take the fourth derivative, I get sine x. Okay, but I already had sine x, so it means that this block will repeat. Okay. So the coefficients will be 0, 1, 0, minus 1, 0, 1, 0, minus 1. It will go up to infinity. Okay, so the Taylor series then sine x is equal to 0 plus the first derivative times x. Then for x squared, the coefficient is 0. For x cubed, the coefficient is, okay, so let me write this then, f of x, or rather sine of x. Sine of x is equal to summation n equals 0 to infinity. The nth derivative at 0 divided by n factorial x to the nth for all x in R. Okay, so here I come, this is the third derivative, so I'm talking about x cubed. It should be divided by 3 factorial, and the number here is minus 1. Okay, so minus 1 over 3 factorial x cubed. Okay, so it will go on like this. Then 1 over 5 factorial x5 minus. So the general term we can write easily. X to the 2n plus 1 Okay, let's check with this one. Okay, that holds over 2n plus 1 factorial. Okay, so this is the Taylor series of sin x. Okay, so you see I have only odd powers here. Okay, so that's why if a function satisfies the property f of minus x equals minus f of x, an odd function. Okay, we could have given it a different name, symmetric, antisymmetric. Okay, those names are more appropriate to describe whether the function is symmetric around x equals 0 or not. But you see that oddness comes from these odd powers. You don't have any even power. So that's the source of the name odd function. Now I can do the same thing for cosine x, because you see that this time cosine x will be this block will repeat. Okay, or I can take derivative of both sides. Remember that it is allowed. Okay, you can differentiate an power series by differentiating it term by term and adding. Okay, using this, we have cosine x equals 1 minus, you see 3 comes here, cancels with the 3 here, you get 1 over 2 factorial x squared, plus 5 comes here, cancels this, so I have 1 over 4 factorial x to the 4 minus, and the general term is x to the 2n over 2n factorial. Okay, so this is an even function. You have only even terms here. Okay, so let's also, not all functions are such nice functions, so let me give an example. Okay, now consider this function f of x equals e to the minus 1 over x squared if x is different than 0, 0 if x equals 0. The graph of this function is something like this. So you see that it is symmetric around x sub around 0, because whether x is positive or negative, it will take the same value. And as x goes to infinity, it goes to 0. Okay, because you see this is 1 over e to the power something. So it is less. It is always less than 1, but it goes to 1 asymptotically. So let us do this. X, y. This is 1. So the function is something like this. Okay, so this is y equals f of x. So it's a very nice function. Okay, except that its behavior at origin is not as nice as it looks. It's not analytic at the origin. Okay, check that. So this is some calculations that you have to do patiently. Check using lots of L'Hopital. The nth derivative of f at 0 is equal to 0 for n equals 0, 1, 2. N equals 0 is this one, of course. You take the derivative of this, so you get an expression. So if I remember correctly, then if you change parameters, instead of x, if you use 1 over x as your parameter, and then the expression becomes simpler, then you use L'Hopital to take the limit, you get 0. Okay? And then, of course, the second derivative is more complicated. The third derivative is even more complicated. You make a guess about the form of the nth derivative. The nth derivative will be a polynomial of this divided by some polynomial in x. So you'll have several such expressions. Then, so you show that in that case, again, the limit, if you have such an expression, using L'Hopital, you show that the derivative is 0. So it's some long calculation, but you don't use anything deeper than L'Hopital. So that's why I'm checking this. But now what does this say? All derivatives at 0 is 0. So if you write the Taylor series is identically equal to 0. Because Taylor series uses only these numbers to approximate the function around that point. Okay? Hence, the Taylor series of f, which is summation n equals 0 to infinity, the nth derivative at 0 divided by n factorial xn is equal to identically 0, because all of these things are 0. Okay? But clearly, f of x is not identically equal to 0. So here the Taylor series associated to the function converges everywhere, okay, but it represents the function only at one point. Okay, so this function is a C infinity function, but it is not analytic at the origin. Anywhere else, obviously, it is analytic. If you write the Taylor series here, it is analytic, but not at the origin. Okay? So this function is C infinity, but not analytic at x equals 0. Okay? So you say, well, we have only just one function, we can ignore it, but add sine x to this function, okay, you obtain a C infinity function, which is not analytic at the origin, because at the origin, the Taylor series you write will be that of the sine function. All contribution from this function are 0 at the origin. So again, at the origin, the Taylor series does not represent sine x plus f of x. So take any analytic function, add it to this one, it ruins the function. Okay? So in fact, there are more non-analytic functions than analytic functions. Okay, let's play a game now. How to estimate E with an error less than something. Okay, so we have this number E, which we naturally developed as the inverse of logarithm. Okay, so you calculate the area under the curve y equals 1 over x from 1 to some point, and the area is equal to 1. Okay, so that point is E. Okay, so what is the value of this number? Okay, so next game is estimating E. Of course, we will do this with an error less than something. So for this, first we need an upper bound for E. Okay, so remember we erased them here, but not here. It's here. The nth derivative, if the nth derivative is bounded, then we'll be able to understand the error term. Okay, so you can do this in several ways. So we can do this in several ways. So one of them is playing like this. So you have this curve y equals 1 over x. You start from here, add these boxes, and, well, here, okay. Now I can add these boxes. They will give me harmonic sum, okay. And at the point, so the area under y equals 1 over x is equal to 1 from x equals 1 to x equals E. Okay. So you try to find how many of these boxes I add so that the sum is larger than 1, and you stop at the first integer when the sum is larger than 1. Okay, so that integer is then, so if this is the integer, for example, this is m plus 1, this is n. Okay, So if you add these things up to here and you show that the sum, of course you do this by trial and error, the sum is less than, is larger than the area, the one, okay, then you take that as an upper bound. So the second one is use e to the x equals 1 plus x squared over 2 factorial plus x to the n over n factorial plus etc. Then, okay, so we will use this one. Then e equals 1 plus 1 over 2 factorial. Okay, so this goes on like this. Okay, so let me show how we do this one. Here we have to do lots of calculation. But again, you get an upper bound, which is 3. So here I'll get an upper bound, which is 3. Okay, so let's see what we have here. Okay, so first note, first recall, so such inequalities are important. N factorial is always larger than, okay, 2 to the n, 4, and larger than or equal to 4. Okay, so you do this by induction. It is true for 4. Okay, 24 is larger than 16. 2, 4, 8, 16. Okay, so it works. And for induction, when you are going to the next step, you are multiplying this side by 2. You are multiplying this side by n plus 1. Okay, n plus 1 is larger than 2. So the inequality keeps growing. Okay, so this holds. So let's see now. We have e equals 1 plus 1 over 2 factorial, 1 over 3 factorial, plus other things. And here I'll stop. Okay, so let's see, 1 over 4 factorial plus etc. So on this part, I approximate this. Each n factorial is larger than 2 to the n. Okay, so 1 over factorials is less than this. So I have, this part is unchanged. 1 plus 1 over 2 plus 1 over 6 plus here, let me see, I wrote this summation. So instead of each of them, so replace each 1 over n factorial by 1 over 2 to the n. Okay, so now this time, this one is less than this. Okay, so this is summation. I start with n equals 4 to infinity 1 over 2 to the n. Okay, so you see suddenly from a hopeless looking series, I come to a series which I can add up. Okay, so this number here, so this part is equal to, well, let me skip this calculation. This part is equal to 1 over 8. Okay. And this part, okay, so then we have e is obviously a positive number. It is less than 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 8. Okay, so if you add up these things, it will be 67 over 24. All we need is a number here. Okay, so this is, you see, is less than 3. Okay, so 3 an upper bound. 3 is an upper bound for E. Okay, now next we use Taylor theorem. Okay, so we add up these things, the remainder in using this Taylor series at the point 1. Okay, so this is equal to the nth derivative of e to the power x is e to the power x. I evaluate it at some point c between 1 and 0. Okay, divided by n plus 1 factorial to the power 1, 1 to the power n factorial. Okay, so 1 minus 0 to the power n plus 1. Okay, so that's 1. Okay, so for some c between 1 and 0. Okay, so the power series, you see this is here x sub 0 is 0. Okay, so when you are looking for error, when you are looking for the error term, c is a mysterious point between your x and x sub 0. Here x is 1, x sub 0 is 0. So this c is a number less than 1, positive and less than 1. Okay, so less than 1. So this thing is less than e over n plus 1 factorial. And this is the reason why we try to find a number here. Any number would work. So 3 over n plus 1 factorial. Okay, now we can go back and say, how much precision do you want to calculate E? Okay, so I want to make this less than, well, let me look at my calculation. So this is minus 6. So we force this. And this is where we write the precision we want. Okay, so I wrote 10 to the minus 6. You can write 10 to the minus 12 and get a better expression. So what we do is find n by trial and error. Don't try to find an analytic expression, because an analytic expression will be a real number, and then you'll approximate to the next integer. So just try integers. N factorial grows very fast, so you don't have to try many numbers. After a while, you'll find an n here, which makes this inequality correct. Okay, so in our cases, let's see, 9 works. Okay, so in our case, in this example, with this error term, n equals 9 works. Okay, so you divide 3 by 10 factorial, it is less than this. You just calculate this, okay? So I'm not going to do that. So E is approximately 1 plus 1 plus 1 over 2 factorial plus 1 over 9 factorial. So we calculate. So you see that now everything is under control. We have a finite sum. Okay, so that's the strength of Taylor's theorem. Something you want to calculate is equal to an infinite sum. Obviously, we are not going to sum this infinite thing unless it's a geometric series where we know the answer, or it's a telescoping series, and if we can write it as a partial sum, which is not easy. So these are the only special cases. In general, you have an infinite series. And Taylor's theorem says that if you want to add these terms with a certain precision, then you can find how many terms you have to add, and then it will be guaranteed that the sum minus this number here is less than your epsilon. Okay, so this number is a huge number here, 98,641 over 36,288. Anyway, this approximates to 2.71828 and then 1526. Okay, so in these calculations we are sure of this part. So actually you see that this one repeats here and then some other things, but we don't memorize it. So you see, by changing this number from -6 to some other things, you'll get larger n's, and then you get a better approximation for E. Okay, so this was, as I told you before, one of the major achievements of calculus, because for navigational purposes, for cartography, you need to find values of sine. In particular, sine of 1 degree was important. And now you have an analytic way of exactly doing this without doing any measurements. Okay, so that one we did. Okay, so let's do Taylor series of another function. Okay, so we have time. So this time, the function is simple. It's not a transcendental function. The function is 1 over x. So you don't need a Taylor series to calculate it. But here we want to demonstrate how Taylor series behaves with respect to singularities. You see, 1 over x is a nice function, but it's not defined at origin. So if you want its Taylor series of f of x equals 1 over x at x equals 2. Okay. And does it converge to the function? You have to do that. Okay. Okay, so here we have f of x equals 1 over x, and f of 2 is equal to 1 over 2. Okay, so we start the same thing. We do this. This is almost always the case when you start writing the Taylor series of an unknown function. You start writing these things. Okay, if you see a pattern, you have the exact formula for the Taylor series. If you don't see a pattern, then okay, you already calculated the first few terms, so you try to work with them. If you are lucky, it will be an alternating series, so at least you know how much error you are making when you stop where your calculation stopped. Okay, so the first thing is, the first derivative is, I write it this way because then it's easy to see what's happening. F prime 2 is equal to minus 1 over 4. Let me do one more. Is equal to 2x minus 3. 2 is equal to 2 factorial over 8. I start to see some patterns. Okay, so the nth derivative of x I can write easily from here. First of all, it's going to be plus or minus. Here you arbitrarily write n and then check if it agrees with this. If it doesn't, then you make it n plus 1. Okay. I observe that I'm bringing down these numbers, so I obtain n factorial here, and I divide it. And here it becomes, you see, this is 2, this is 3, this is 1, this is 2, so this is x to the power n plus 1. Okay, so this is, you check that. Okay, now by induction, you take the derivative of this and see that the n plus first derivative obeys this pattern. Okay, and then, of course, the value of this at 2 is equal to minus 1 n factorial 2 to the power n plus 1. Okay, so these are our coefficients. These are Cn. Okay, so Taylor series Taylor series is summation these things minus 1 n factorial 2 to the power n plus 1, and here I write x minus 2 because I'm evaluating this at here to the power n equals 0 to infinity. Okay, I have a Taylor series, I have a function. Does this Taylor series converge to the function? I look at the error term. The error term, you see, is going to be something like this, except that I'll have n plus 1 here. Okay, so suppose we stop at n minus 1. So the error is the nth derivative evaluated somewhere here between, between x and 2. Okay, so here you have 2 to the power something. So here, close to 2, it will converge. Okay, so this will go to 0. So it will converge. Okay, so what else? Okay, so let's do that and see what we can do. So okay, let's say using Taylor's theorem, the nth derivative, the remainder after this is equal to, okay, let's look at the absolute value. So I don't want this. The n plus first derivative comes with n plus 1 factorial divided by 2 to the n plus 2. Okay, so this is the, okay, so maybe I write the general formula here and then we put the, so I'll have n plus 1 derivative evaluated somewhere divided by n plus 1 factorial times x minus 2 n plus 1 for some c between x and 2. Okay, so now I know what this is, so I'm taking absolute values here. Okay, this absolute value is enough. So this one is n plus 1 factorial divided by 2 to the power n plus 1. Now c to the power, c to the n plus 1. And what else? Okay, I divide this by 1 over n plus 1 factorial, and I have x minus 2 n plus 1. Okay, so these cancel. Okay, so I have to, so why did I get this funny thing now? X minus 2 n plus 1 over c to the n plus 1. So when n goes to, when x is, okay, so I want this to be x minus 2 over c. I want this to go to infinity. Okay, so for this thing, x minus 2 over c must be less than 1, right? So x minus 2 over c less than 1. So this is x minus 2 over c less than 1 larger than minus 1. Well, I don't know what c is, so if I add 2 minus c, x, 2 plus c, so the calculations are getting out of hand.
Approximating alternating series?
Hmm?
Shouldn't we use approximating alternating series?
Yeah, the series converges. We don't have a problem with that. I'm trying to check if the, according to Taylor's theorem, the remainder goes to 0 or not.
The error should be the n plus 1.
Mm-hmm. No, okay, so the series converges to some function. Okay, so if I use the first n terms, the error is less than the n plus first term. But what is that function? Okay, so that we are claiming that that function is 1 over x. Okay, and for that I wanted to use Taylor's theorem, but somehow I missed something. So after I missed it.
Shouldn't we say c to the power n plus 2? Or am I missing something?
Here? Okay, so I'll do this calculation. I'll complete this calculation on Thursday. Okay, so I'll check this later. Okay, so I'm erasing this. Okay, so I'll show that this function converges to f of x at around here. Okay, so here I didn't do the calculations, but here we know that this converges. Okay, so I'll show later. That the Taylor series converges to 1 over x Okay, but we can now show that the series converges on some interval, okay, on some interval. So this was actually the only reason why I did this was to show that this is not convergent everywhere, only on some interval. Okay, so we take, okay, so you take this part as an, actually it is anx, but let's call it an. Use ratio test. We look at an plus 1 over an, absolute value, and we take the limit as n goes to infinite. Okay, so limit n goes to infinite. So, well, you see this part is, I'm skipping the minus 1 to the n because I'm taking absolute value. So this is n plus 1 factorial divided by 2 to the n plus 1. Nobody is warning me that I wrote the Taylor series wrong. That's why this totally trivial calculation did not work. Okay, so what is the coefficient? Okay, so let us write, this is f. So what is the Taylor series? General form, n equals 0 to infinity. So what do I write here in front of x minus 2 to the power n? Over n factorial. Right? We forgot the n factorial, so nothing converged. Okay, so f n at the point 2 divided by n factorial. Okay, so summation n equals 0 to infinity. This is, I have minus 1 to the n. 1 over n factorials cancel. You have 2 n plus 1 x minus 2 to the power n. Okay, so this is the Taylor series. Okay, so now we can apply Taylor's theorem. Okay, so because Taylor's theorem must be simple. Okay, so here you see here you don't have any factorials, so this thing would be simple. I'll do it in a minute, but let me start with the remainder theorem. Okay, so remainder. So use Taylor's theorem. Remainder x at absolute value. So what is this? This is the derivative n plus first derivative at some point c divided by n plus 1 factorial times x minus 2, so absolute value to the power n plus 1. Okay, so I hope the calculation now works. So this thing is n plus 1 factorial divided here, n plus 1 factorial divided by c to the power n plus 2. Okay, so I wrote this one, right? I hope this time I wrote it correctly. Okay, so I divide it by 1 over n plus 1 factorial. So I again obtain the same thing. Okay, x minus 2 n plus 1. Okay, so again, at this point, I have no idea about how to proceed. So this thing will go to 0 when x minus 2 is less than c. C is between x and 2. Okay, so I'll finish this on Thursday. Okay, so I'll do this next time. Okay, so here I did something else, so I'll skip. Okay, so the next thing is, so you see we have Taylor series for sine x and cosine x, but we don't have Taylor series for tangent x because that requires some complex analysis. But we can still find the first few terms of tangent x without actually taking derivative. The problem with the Taylor series of tangent x is that if you start taking successive derivatives of tangent x, you get larger and larger terms. Because you take the first term, you get first derivative, you get secant x. When you take the derivative of secant x, you get secant x times tangent x. And from there on, you have a product. The derivative of a product splits into two. And each term is a product. It goes into two. So when you come to the nth derivative, you don't see any pattern. Okay, so nobody sees any pattern there. So there are other ways of obtaining the general term, which involves Bernoulli numbers. But we don't do this in calculus. Instead, in calculus, there is a cheap way of obtaining the first few terms of this, as many terms as you like. So that requires multiplication and division of power series. You write the Taylor series of sine x divided by the Taylor series of cosine x. That will give you the power series of tangent x. But division is generally done in a tricky way by multiplication. Okay, so we'll first do multiplication of power series. So if you want to multiply these things, an x to the n equals 0 to infinity, I want to multiply this by summation n equals 0 to infinity bn x to the power n, and I want to obtain summation n equals 0 to infinity cn x to the n. Of course, we can't multiply infinitely many things, but you observe that, for example, if you want to find out the coefficient of x squared, then here you only need a0, a1x, and a2x squared. X cubed, x to the 4, here and here, will not contribute anything to the coefficient of x squared. Okay, so then this thing boils down. Every time you want to find a Cn, you multiply a polynomial by a polynomial and take the largest term. Okay, so that that gives us Cn is equal to, okay, if you multiply two polynomials, how do you obtain the power, the coefficient of a certain power? You multiply all terms here with the terms here so that their powers add up to n. Okay, so this is summation k equals from 0 to n a k b n minus k. Okay, so this is just polynomial multiplication. Okay, so we don't have time now, but on Thursday I'll give examples for these. Now, division is easily obtained as a multiplication as follows. Okay, I want to divide this n equals 0 to infinity a n x to the power n over summation n equals 0 to infinity bn x to the power n, and I will obtain a power series n equals 0 to infinity cn x to the n. First of all, for this multiplication to make sense around x equals 0, so you see I expanded Taylor series around x equals 0. So this thing must not be 0 at x equals 0. At x equals 0, the value of this is b0, b sub 0. So b sub 0 must be different than 0. Otherwise, you can't, this division doesn't make sense. Then you take out an x. Okay, so you are talking about 1 over x or 1 over x squared. Okay, so if this is the case, this is equivalent to say that summation bn xn times summation cn xn is equal to summation an xn. I know these, and I will find this as follows. You start with n equals 0. Okay, so b0 C0 is equal to A0. So here you can solve C0 because B0 is different than 0. So you can divide by 0. Next you write B0 C1 plus B1 C0. This is equal to A1. But now I know C0. Okay, I found it here. So here this was unknown. I solved it. Now here the only unknown value is this. I solved it. Let me do one more, then it will be clear. B0 C2 plus B1 C1 plus B2 C0 is equal to A2. Here you see that I calculated this and this. The others are given. This is the only unknown. I solved it. Okay, so you keep doing this up to the point you say enough. And that gives you the first few terms of the Taylor series. Okay, let's stop here. On Thursday, I'll continue from here.